My name is Iris Seaman. This is work that I started at Brigham Young University with David Wingate. And this is work that I've continued to improve at Northeastern University, where I started my PhD with Jan Willem van de Meent. I'm grateful that today I'm able to present this work during my absence of leave. I'm taking some time off to raise my new baby girl who's about 6 months old now. So this presentation is nested reasoning about autonomous agents using probabilistic programs. I'd like to start off by introducing a realistic scenario people generally experience. One of a driver in an automobile encountering a pedestrian. Now, in this experience, although one may not realize, the driver asks questions he or she must answer quickly. Quick but important questions include, is this pedestrian going across the street at this very moment? And did the pedestrian see me? Can I keep on driving? Questions such as these can be generalized into questions such as, what are the intentions of other agents? And what do other agents know about the world? Which in essence can be nicely wrapped into the specific study of theory of mind, where we are consistently trying to figure out what the beliefs of other agents are. Beliefs as well as intents, desires, and goals. Today's work that I will be discussing with you is motivated by an idea in reinforcement learning known as RL, where there is an assumption that all agents in a multi-agent environment are acting optimally. So in the case where we are trying to reason about other agents, we can argue that RL does this implicitly. And this talk is going to present a model that reasons about other agents in an explicit manner. And this is done in order to remove that assumption and work in a scenario where agents act optimally, where agents acting optimally may not be the case. This work is focused on a particular problem in order to demonstrate a very concrete application. Now, bear with me as I set the story. Imagine a setting of a city with many streets intersecting with one another, many buildings to obstruct vision, and in the city, as you can imagine, many interactions taking places with many different people. I like to focus on this one scenario, a bank robbery. Now, naturally, the authorities are alerted thanks to an alarm set off by the crime. However, there is a caveat. We set the location of where the bank robbery took place and the starting location of the authorities to be at a distance from one another, meaning they are far apart from one another, and this can be very, very far away considering the size of the city. So, I'd like to take a look at these two characters I just introduced. The authorities can be labeled as a chaser. The chaser's objective is to intercept the runner before the runner reaches its unknown goal location. And the robber can be classified as a runner, whose objective is to reach his goal location before being detected by the chaser. Now, with these two characters who are clearly opponents to one another, we can imagine a flow of thoughts coming from each of them attempting to outwit the other. Once an agent can settle with the conclusion of what the other agent's plan is, only then can they make their own decisions of what they should do in order to complete their objective and essentially win the game. As an example of what this looks like in a particular scenario, we can imagine that the robber has an escape plan to get to some location unknown to everyone but himself. And the robber knows that the cop knows that he has a plan, so maybe change the plan. But the authorities, she knows that the robber has a plan. She also knows that he knows that she knows that he is going to try to outsmart her by changing the plan. Already, we can see how this can get a bit confusing and complicated. It has definitely given us a headache late in the day thinking about how we should approach such a problem. Well, to simplify this train of thought, we illustrate the problem with this example of recursive thinking. We show here a map. the map shows a building of a bank at the bottom with the robber's safe house up on the right. The marked dotted path can be an example of a trajectory of how the robber plans to complete his objective. A trajectory demonstrating the authorities' quickest way to get to the bank is shown on the left. This is an example of a very naive plan on part of the authorities, and that is the quickest route to intercept the robber. Perhaps a path she could take to increase the probability of intercepting the robber would be this one instead. A longer path, not as direct, but perhaps wiser since it does go down the center of the map. This is an example where she used theory of mind by choosing new decisions that adapt to a more probable outcome based on the prior knowledge of what may have happened. Now, let's turn this around and ask, how can the robber use similar logic to perform the same kind of nested reasoning? If the robber were to answer his own question of what she would do if he were to run straight home, then he could adapt as well and decide that his plan would be choosing another path, perhaps one further away, less visible, or with less traffic. As you can see, the depth of recursive reasoning like this can go on and on. However, we want to demonstrate that many layers of recursive reasoning is not required to achieve rational behavior by agents exposed to a scenario such as this. To model such nested reasoning explicitly, we design our models in a layered fashion. We begin with a model that describes the perspective of a chaser. And we do this by making the chaser the outer layer of our model, where it will describe the chaser's high-level beliefs of the current situation. Then we show that the chaser will model the runner. And we call this the middle level. It describes what the chaser believes about the runner. Then we conclude with the last layer, our inner model, where we describe what the chaser believes about what the runner believes about the chaser. And we stop layering beliefs at this point. We do this to demonstrate that a simple layer methodology is enough to produce rational behavior that demonstrates the practice of theory of mind. We also do this to avoid, intractability as we add more layers. We use a planning-as-inference formulation. What this means is that we are basically turning a planning problem into an inference problem. This pi of x is a target density that we want to know. And this pi of x can be written down to a proportion of some kind of reward and a prior distribution. What we want to happen in this probability density is for there to be higher probabilities in situations where we get higher reward and low probabilities where we get low reward. And then we have that prior that describes the probability under the world dynamics. So now we ask ourselves, what would be a situation that would produce high rewards? Here on the left, we illustrate a runner modeling a chaser. Here the runner evades detection. On the right, we illustrate how a smart chaser that uses that model of the runner can use the runner's plan to choose its own better plan that will increase the probability of detecting a runner that believes will evade detection. As you can see, this is an example of high probability for the chaser detecting the runner. Thus, high probability equals high rewards. Now we ask, what is an example of what low probability looks like? On the left, we illustrate a runner that again evades detection from the chaser, however, using a different plan from our previous example. Instead, the runner runs around the city to reach its safe location. On the right, we show that the chaser has again adjusted its plan to go down through the center of the city. And since the chaser's modified plan does not improve detection, the rewards for detection are low, thus low rewards, low probability. The next question we asked ourselves was, what should rewards look like then if we want to have the probability distribution to be described as such? Well, since we are basing our probabilities on visibility in a time-dependent game, we design our reward model to care about the number of times our runner expects to be visible, while imagining his outsmarting situation as the middle model, as well as the number of times the chaser, the outer model, expects the runner to be visible. Using this formulation, we will now see what happens in situations where we have high probability. Well, we see that the runner expects to be seen in low number of times with the chaser. We see that the runner expects to be seen a low number of times with the chaser expecting to see the runner a high number of times. And so in that case, we have high number minus a low number equals a high number. And so a high number means high probabilities. So that makes sense, and that's what we want to happen. Well, how about in a low probability situation? Will this formulation work for us? The runner expects to be seen a low number of times where the chaser expects to be seen, or the chaser expects to see the runner also a low number of times. We have a low number minus a low number, which equals an even lower number, and that lower number basically means a low probability, and that again works for us. But something interesting happens when we introduce the case where the runner happens to choose a path that results in a high detection count, as shown on the left. The runner knows that he is going to be seen by the chaser a high number of times. So when the chaser uses that model, the chaser thinks it does a great job, where she easily detects the runner. But in this case, the runner performed poorly when it came to rational decision making. So when this happens, let's say the number of times each expects to be seen is equal, the reward turns out to be 0. And suddenly, because of our formulation of the reward model and our final density, we end up relying on the prior distribution. Okay, so moving on to making this scenario a bit more concrete. For our experiments, we use a three-dimensional environment consisting of a point cloud of the city of Bremen, Germany, which we flattened out to two-dimensional and turned it into a polygon map which allowed quick computations. And we asked ourselves, how are we going to get agents to behave? We decided to have agents plan using an RRT, which stands for Rapidly Exploring Random Trees. What RRTs do for us given 2 points is give us a random path between those 2 points, which can be produced, or what can be produced is a path that travels down the center of the city. Another path that can be produced may instead travel around the city. And since the RRT provides random paths between these 2 points, it naturally becomes a distribution over paths, which is neat because then we can later smooth out the noisy paths produced and control walking speeds for time step simulations. The next technicality we require is the ability to determine visibility, since we require the number of times visible for a reward model. And we do this by using an isovist, which is a limited field of view that describes everything which can be seen by an agent. And this lends itself nicely to be built within the probabilities models we require. What we do is use a nested importance sampling scheme. And we start off with an episode which iterates through each time step. For each time step, the agent performs inference. In the case of the chaser, she generates K samples for her possible, planning, her possible plans. And for each of those K plans, she now samples L cases of what the runner might do. So that gives us K times L samples per time step. We then perform resampling, which allows us to keep the best versions of those samples, and that gives us a variant of a particle filter. Lastly, I'll discuss the experiments for this work. So we have this explicit model of reasoning about reasoning. And naturally, we wanted to see if these agents perform rational decisions as they try to complete their respective objectives. We asked ourselves, what happens in our model of our chaser model, modeling a runner, modeling a chaser. So if we have a runner that's modeling a chaser that is going down the city, what we get is a distribution of a runner going around the city. And that turns out to be useful as the chaser now uses the runner's distribution to maximize detection. As we see, the chaser's distribution of path adjusts to go around the city as well, thus maximizing visibility or maximizing the probability of detecting a runner who has adjusted his plans. One of the most fun experiments we did was simulate games of these two character agents. And this experiment was mostly answering the question of whether something like this could be put into practice. Can we simulate agents in episodes to perform theory of mind as they travel the map and try to complete their respective objectives of either evading detection or detecting the other? And not only can they do this, but answering questions such as, is this effective? Can agents performing theory of mind outperform agents that do not? We played with various models in order to answer these questions. I'll briefly describe the ones we chose to work with. We begin with what I call the smart chaser. And this smart chaser uses a model of a naive runner. So we tested just how well this model would perform when challenged with a naive runner. We ended up with an average of 98% detection rate. That was awesome. We then performed a similar experiment using the smartest chaser, which is our theory of mind model. Since the smartest chaser uses a model of a runner modeling a chaser, we challenged it against a smarter runner, which did use a model of a chaser. In this case, the average detection rate was 56%. What was interesting about this was when we started switching the models to challenge agents that were not quite what they were modeling, the detection rates adjusted quite nicely. When we challenged the smart chaser with a model of a naive runner against a smarter runner, one with the model of a chaser, the smart chaser performed as expected. It decreased to an average detection rate of 36%. It performed well when it expected a less prepared runner and poorly against a runner that thought about the chaser's beliefs. Now, this is the interesting part. When we paired our full-blown theory of mind smartest chaser against a naive runner, one without any modeling of its own chaser, or in other words, the chaser model has a model of a smart runner, but it's going against a runner not as competent. It performed just as well as when it was against a more prepared runner. Therefore, our theory of mind chaser performs well against all lower levels of runners. Lastly, I show how varying sampling budgets affected our nested inference results, or more precisely, how it affects our rewards at each of the time sets our experiments simulated. Recall that we use K samples for our outer model, which for each of those K samples we produced L samples. What we saw was that if we had too many samples on the outer model, our estimates of the rewards had higher variance. However, when we had more models of the inner model than the outer model, we had better estimates of the rewards. To conclude, I'd like to state that this planning-as-inference approach is a really intuitive and effective way to set up a problem where we have agents that cannot carry the assumption that all agents act optimally as it is in reinforcement learning problems. Additionally, this approach is effective to describe high reward trajectories that give us high probabilities. And when it comes to these nested models, probabilistic programs provide stochastic simulations of trajectories. And that concludes our presentation. Thank you very much.